to our presentation. Our third title is Generation of Multi-Agent Ignition for Object Transportation using Deep Reinforcement Learning and Blend trees. We are from National Yangming Jiaotong University, Taiwan. This is the outline of the presentation. We'll first give an introduction of this paper. The motivation of this paper will be mentioned in this part. Some related work will be presented later, and we'll have a look for the system overview and the method. Finally, the experiments and result and the conclusion will be reported. And let's start the introduction. Character animation generation is an important topic in computer graphics and virtual reality. Multiple characters performing collaboration behaviors enrich animation content. There are agent-based methods which animate multiple agents transporting objects. However, they are rule-based or agents are treated as rigid bodies. Recently, deep learning methods have been adopted for character animation. So, our idea is to adopt deep reinforcement learning and blend tree, which is a kind of motion blending structure to generate animation of multiple characters in object transportation. We propose a framework to integrate deep reinforcement learning and blend trees to control human-like characters in object transportation. We use several examples to demonstrate our method. This video clip shows an agent using passive objects to satisfy predefined constraints. The detail of this clip will be discussed later. Okay, and we present the related work. Deep learning techniques have been proposed for physical-based character animation. Furthermore, agents are simulated to play hide and seek. However, the object is attached to an agent while the agent carries it. Then the following is the system overview. An agent can perform three skills: navigation, mesh manipulation, and adjustment. We use one policy for one skill. The agent can push a passive object to a goal while satisfying the constraints. The red item on the object is a text information in fraction form. The left side is the numerator, which indicates how it indicates now there are one agent dealing with the text. And the right side is the denominator, indicates at most one agent can deal with the text. In this picture, a goal is placed as a green cylinder. Position constraint as the passive object should be pushed as close as possible to the goal. Moreover, the yellow arrow on the top of goal indicates the predefined orientation of the goal. Also, some obstacles are put in the environment, so the agent needs to avoid them. Each goal has two constraints, which are position and orientation constraints. When the two constraints are satisfied for the passive object, the goal is finished. The position constraint CP asks the agent to make the position of object J close enough to the position of the goal. In the meanwhile, the orientation constraint CA defines that the orientation of object J should be close to the X orientation HG. Our system has two processes, learning and simulation. In the learning process, a policy is learned for one skill. So, in total, there are three policies to learn. After the three policies are learned, we apply them to control the agent to perform tasks. The most appropriate policy is to select for an agent at a moment. For example, when an agent is near to a passive object, we apply the push skill. When the passive object is near to a goal position, the agent tries to adjust its orientation. The agent follows a workflow to perform skills. The agent starts to find a passive object and push them to the goal. When the constraint CP is made, the agents try to perform the adjustment skills to satisfy the constraint CA and CP. The navigation skill allows an agent to navigate. Furthermore, it controls agents to move away from a route. The character E on the top of this agent means the agent are trying to escape from the scene. We'll see another demo for the evacuation scenario. The push manipulation skill allows agent to push an object. Also, the adjustment skill allows agents to adjust the orientation of an object to satisfy the orientation constraint CA. A blend tree uses blending parameters to compute pose of a character. This is a nest blend tree. Also, these are basic motions of this blend tree. Our system uses a simple hierarchy of blend trees for animating characters. Here, this is a 1D blend tree, which uses one blending parameter to compute the pose of character based on motion pairs. Each motion pair has a coordinate which indicates the exact pose of the character when the value of blending parameter is equal to the coordinate. Thus, the pose of the character can be interpolated based on the motion pairs. This example shows a blend tree consisting of 3 motions: idle, walk, and run. This is the blend tree structure in our system. Motion pairs include left strap, right strap, walk, run, and push. The blend trees use 3 blending parameters to determine the pose of a character. 2 of them are used for movement poses, and the third one is used for poses when a character pushes an object. Then here's the part for method. We employ reinforcement learning to learn the policies. In the learning process, a policy is learned to control an agent to perform an action based on the agent state. After the agent action is applied, the agent receives the reward. The idea is to maximize the long-term reward of the policy. Here, we use PPO and SAC trainer. The action of an agent is represented as 4 values, which are used for determining the movement direction and the pose of the character. 3 of them are used for blend trees to performing moving and push. The last one is to determine the y-axis rotation. An agent state is a series of observations. The system contains 3 consecutive observations as one state of the agent. This table is the item of an observation. The agent relies on the items to know the environment, target, object, and the goal. The IVI here is the velocity of agent I. The information returned by a ray is a tuple contains an indicator for the tag of hit object and the hit version which indicates how far the ray hit object. The ray cast stack R contains several rays information. Please refer to our paper for details. This table shows the items that are used in the policy. For example, the policy uses navigation. The policy for navigation uses relative velocity and ray cast stack. And this is the environment used for learning the navigation skill. There are walls, obstacles, agents, some regions are marked as dangerous. The agent navigates in the environment to search for passive objects or other agents. Please refer to the paper for details about the learning environment. This table lists reward terms. The reward terms encourage or discourage the agent to perform an action under different situations. For example, the goal will encourage the agent to push the block to the goal. Also, the collision will discourage the agent to keep away from the obstacle or other agents. This table shows the reward terms that are used in the policies. Then, we report the results. We implement our method on Unity 3D and use NL agent toolkit. This video shows agent using several passive objects to predefine goals. We can see that the objects are pushed to the goal first, and then the agent adjusts its orientation. This video shows the evacuation scenario. The agent moves away the obstacle to send the evacuee. The N on agents means navigation, and the X on the top of some agents indicates that they are evacuees. After the obstacle are pushed away, they can escape from this scene. And this is the result for navigation. We investigate the effect of different ray lengths. When the ray length is 15, the coverage region is the best. Also, this video clip shows the effect of some reward terms. The agent does not perform well if a reward term is not applied. And here's another test, an evaluation test on adjustment skill. These video clips demonstrate that adjustment skill under different conditions. We can see the test fails since the agent cannot achieve the orientation constraints. And here comes the conclusion. We present a framework which integrates deep remote learning and blend trees to produce multiple agent animation in object transportation. We use three policies for computing blending parameters so that the policy can control characters to perform navigation, push manipulation, and adjustment skills. And finally, we demonstrate several examples in which the character performs each action and transporting objects. Then, this is the end of the presentation. Thank you for your listening.
Nobody has a question? I have one question. Is all your objects are fixed object? I mean, when I say this, they are, the object cannot have a movement. Do you think you can extend to moving objects?
Yes. Is to moving some object or in this thing, right?
I mean an object that can move by itself.
Oh, yes, this is our next step, right?
Because your object, you push the object, but the object could react. Is it possible?
Oh, I do not think this. Yes.
Hello?
No.
Seems to have some problem, no?
Yes.
Okay. Any other comments or questions?
Daniel, there's questions in the chat if you want to have a look.
There is one, but I lost it.
So,
Yes, yes. Yes, somebody asked if we increase the number of agents, if we increase agent, always we will get the result faster.
I don't think so. But yes, we find that the agent train in only one agent, but we can use that model when they are doing something in collaboration.
Okay. Any other question? Okay, so thank you very much.
Thank you.